Alright, welcome everybody. So during this atomic structure video, I'm going to talk to you about the beginnings of the quantum mechanical model. And this is our current theory of how the atom exists. We use the quantum mechanical model to describe how the electrons are organized in an element. And so these are the goals for this part of the chapter, quantum mechanics. I have this separated because I used to actually just teach this in AP, but with IB, the fact that I didn't go back and review some of the early atomic structure over the summer with you, I put that in the beginning. So, to get into quantum mechanics, you really have to understand, what we know about light and about the nature of light. And so we see light as this, visible form of electromagnetic radiation. Turns out that there are other forms of electromagnetic radiation that are also considered light that you can see. Things like ultraviolet, X-rays, gamma rays. All of those are forms of electromagnetic radiation, as well as things that are less powerful in energy, like infrared and microwaves and radio waves. So what we know about electromagnetic radiation is when we think of it as a wave, it travels through a vacuum at a speed of 3 times 10 to the 8 meters per second. And that these waves have characteristic features to them. So they have a wavelength, they have a frequency, they have an amplitude, and then they have their speed. And we can relate the we can relate the frequency and the wavelength by using the equation that I have down here that I'll circle for you, where c is the velocity of the light, which is 3 times 10 to the 8 meters per second, and frequency and wavelength, they are multiplied together. So this shows that they're inversely proportional. And you can see that on the next slide here. Here's showing you a wavelength on the left here, or a wave on the left here. It has a certain wavelength and an amplitude. If I push those waves together, I am decreasing the frequency. I'm decreasing the wavelength, but the frequency has gone up. The frequency you can think of as cycles per second. So how many times is the wave passing through a certain point in a given amount of time, which is per second. So let's say that I were to mark this spot right here, and the wave were to move this way. Well, how many cycles per second does the wave, have at that particular point? So if I make the wavelength shorter, the frequency will get higher. Now we could change the speed of light by having it go through different materials like water or air, but in a vacuum, which is what we're going to stick with, the speed of light is 3 times 10 to the 8 meters per second. Now this is showing you over here an amplitude that is lower. And what the amplitude really corresponds to with the light is the brightness. So this would be dim light over here, and this would be brighter light over here. So if we look at these next two waves down here, we have two waves. Let's compare their amplitude to each other. I would say just eyeballing it, their amplitude looks about the same. But then when we look at the frequency and wavelength, we can see over here, this has a shorter wavelength and a higher frequency. And then we could say the opposite here, this has a longer wavelength and a lower frequency. Now, frequency really determines the color of the light. So, if we go back to looking at the electromagnetic spectrum down here, and we do our, Roy, G, Biv, then what we can see is that the violet light over here, it has a wavelength of about 400 nanometers. And over here, the red light has 750 nanometers. So the frequency / wavelength is going to be different depending on the color of the light. When light has a single color, we call it monochromatic. Monochromatic light, a single color. Now the thing is, we're interested in physics and in chemistry about the wave nature of light. But when it comes to discerning, what is the structure of the atom, we really are concerned with another type of property of light, and that's its particle nature. And so when we look at the particle nature of light, it tells us a lot about light's ability to carry energy. And it turns out that, in the early 1900s, Maxwell Planck, he was sort of the father of quantum mechanics because he discovered this phenomenon and sort of explained it for the first time, blackbody radiation. And what blackbody radiation is when you have a solid black object like graphite, or on your oven, those elements if you have an electric oven or an electric stove, when it's heated, it'll emit radiation with certain wavelengths, and that wavelength will correspond to the energy. And what Maxwell Planck did was he came up with this equation to describe the energy that's being emitted. And he has his equation here. The energy is equal to the number of little packets that he saw times his constant, which is an experimental constant, times the frequency of the light. And so I outline that down here. Here's the frequency, Planck's constant, which I give you, the energy, and n is the number of photons. Now, you can't detect a single photon of energy, especially a visible light. Maybe if it's gamma radiation, you'd have more of a chance. But, you can't really detect that. You have a mole of photons usually. If you have a laser that has a certain wavelength, it's giving off a mole of photons. And this is what blackbody radiation looks like. So just to summarize so far, we have two equations. We have, like the wave nature of light, and then we have the particle nature of light. And we could relate them together, E equals h times c over lambda if we want to. We can talk in class about the units for each of these, although they are given in this note packet. So when we look at light now, we say, well, is it a particle or is it a wave? Well, it's actually both things. So here we have the wave nature. So the wave nature, it describes how light goes from one spot to another. If you wear glasses like I do, or if you, ever used a microscope or a telescope, we're basically, bending the light waves in order to either see far away or close up. And we can see that here when we put light through something called a double slit. It will actually cause the light waves to come together in what's known as a diffraction pattern. And so when I look at this, I'll get a bright spot and a dim spot, a bright spot and a dim spot, bright, dim, bright, dim, bright, dim. And I get this pattern. And so we see light waves do this. When we look at the particle nature of light, it describes things like the energy of the light particles, things like the blackbody radiation, and something called the photoelectric effect. And that was really the key experiment that was done by Einstein. And I want to describe that to you now, because that's sort of like the real damning evidence against light just being a particle, light just being a wave. So the photoelectric effect, it was conducted by Einstein, and his experiment sort of proved Planck's idea. So what he did was, very simply, was he shined in light of a single monochromatic, color, and he shined it on a metal. And when this light came in and hit the metal, if the light had a certain frequency, electrons would come off the metal. If light was below the frequency, which you call the threshold frequency, then no electrons would come off. And so he could change the intensity of the light, the amplitude, and what he would see is that unless it had a certain frequency, the photons would never come off. The electrons would never come off. So when I look at this over here, this is sort of a summary of what I just said. You can only explain this effect if you treat light as if it's a stream of particles. If light was acting as a wave, it would be how bright the light was, the amplitude, the intensity, not the frequency. But we saw that it was the frequency. And if we go back to Planck's idea, we have E equals h times frequency. If we increase the frequency, we increase the energy. And this sort of solidified the idea that light existed as little tiny particles, little tiny packets of energy. So light comes in, it shines on a metal, electrons are ejected. But there's some little details about the photoelectric effect which I outline on the next slide. And I want to just go over them. And you really need to know these. So unless you use light that has a sufficient frequency called the threshold frequency, then no electrons will be ejected. And this is because if we think of photons as little particles, the photons would come in. They would hit the metal. There's electrons on the metal surface. And if those photons don't have enough energy, they can't transfer that energy to the electron and get the electron to be dislodged or ejected. So the photons need enough energy, which is related to its frequency. If we increase the frequency, then the photons, the little particles, have more energy. When they each hit an electron, they will transfer that energy to the electron, and the electron will be ejected. Now, if you increase the brightness, all you're doing, if this was dim, all we're doing is we're just adding more photons. The energy of the photons doesn't change. So if we add more of those photons, we'll have either a lot of low energy photons or a lot of high energy photons. Either way, each photon, either it will be able to eject electrons or it will not be able to eject an electron. So the explanation of this, is that light exists as particles. The energy of these particles depends on their frequency, not amplitude, that's associated with each of the photons. So if you're using light of a sufficient frequency, then as you increase the intensity, the brightness, the number of electrons ejected increases, but their individual energies do not change. And so that shows what's kind of up here again. You have either a few photons or you have a lot of photons. The brightness of the light, it is the amplitude of the wave, but it's also the number of photons coming in. So now you have more photons, and either those photons will eject more electrons, or if they don't have sufficient energy, they won't eject any electrons. Now, as we increase the frequency above the threshold frequency, what we see is that the electrons that are ejected will have more energy. And you could almost think about this. The energy of the electron is equal to the energy of the photon minus the energy for ionization. So it takes energy to remove the electron. Now, the energy of the photon has a certain amount of energy associated with it. If we subtract how much energy it takes to pull off the electron will be moving with that difference. Sometimes they call this ionization energy the work function. Sometimes they call it the binding energy. It depends on who you talk to. Okay, here's just a look at the photoelectric effect graphically. And so, these are 3 different metals here. And so, I believe so, yeah. Or no, it's 1 metal. And so what they're showing you is that, as I increase the frequency of the light with 3 different frequencies, I will get the electrons coming off at different energies. So the first electron at the lowest frequency that has the threshold, it will come off at a certain energy, and then the next, and then the next. Is that for 3 different substances? No, it is for 3 different substances, excuse me. So this would be my first metal. As I increase the frequency, the metal will come off at higher energy. If I use a second metal, it may have a different threshold, but as I increase the frequency, then the electron will come off with more and more energy. And then if I have my third metal, if I increase the frequency, the electron will come off with more and more energy. So what we're going to do next time is we're going to apply this idea of quantized energy to the atom, and we'll do the Bohr model. Thanks so much for watching.